This is Grothendieck and Serre, and actually I always have to check which is which. It's Grothendieck on the left. This is just about when they met each other. This is going to be very much a talk about the two of them. Around 1949, published in 1949, André Weil conjectured a deep connection between number theory and topology. Around 1953, Jean-Pierre Serre took it on as a project and began recruiting Alexander Grothendieck to work on it. Serre created a series of really concise, elegant tools, which Grothendieck and his co-workers then simplified into thousands of pages of category theory, making it, in Grothendieck's words, tout ce qu'il y a de bébête, infantile in its simplicity. There is a constant problem in translating Grothendieck because bébête can also be a boogeyman. Bébête can be various other things. In context, I think Grothendieck is not interested in playing on words. In the context, I think he sees this as simply meaning infantile. And yet that's not all the word means. It did work. And in fact, Miles Reed, among others, has said that Grothendieck himself can't necessarily be blamed for category theory, since his own use of categories was very successful in solving problems. Grothendieck, on the other hand, Grothendieck's memoir, Récolte et Semailles, makes it plain that he thinks he has been blamed for category theory and for Grothendieckeri in general. Grothendieck describes two styles in mathematics. If you think of a theorem to be proved as a nut to be opened, so that you can reach what he calls the nourishing flesh within, the principle of the hammer and chisel is you put the cutting edge of the chisel against the nut, you strike hard, repeat at various places if necessary until the nut cracks open and you're satisfied. But Grothendieck says that he has a different strategy. He says, I can illustrate the second approach with the same image of a nut to be opened. The first analogy that came to my mind is of immersing the nut in some softening liquid, why not simply water. From time to time you rub so the liquid penetrates better, otherwise you let time pass. The shell becomes more flexible through weeks and months. When the time is ripe, hand pressure is enough, the shell opens like a perfectly ripened avocado. And then he says, another image came to me a few weeks ago. The unknown thing to be known appeared to me as some stretch of earth or hard marl, resisting penetration. The sea advances insensibly in silence. Nothing seems to happen, nothing moves. The water is so far off you hardly hear it, yet it finally surrounds the resistant substance. This is the strategy of the rising sea, the swelling sea. Well, this is another translation problem. The French is la mer qui monte. Again, any of Grothendieck's friends in post-68 psychoanalytic French circles would have seen this as a pun for le amer qui monte, the rising bitterness, and la mer qui monte, the lying mother. I believe Grothendieck is completely unaware of that. On the other hand, it's entirely impossible to translate into English. Are we to take mer here? If we say a rising sea in English, to me this suggests a storm. This image includes storms. If we say a rising tide, well, this image includes the rising tide in French. At any rate, it's this water surrounding.
Subtract that I. You need to know about degree -1 take cohomology in some detail. So when we originally formulated the notion of quasi-regular sequence, we just formulated it like that because that was all we understood at that stage. So the conjecture, and this is just a conjecture at this stage, is that the cohomology ring of a finite group always has a quasi-regular sequence. We don't know whether that's true or not. However, we've checked it in huge numbers of examples. We know that it's true for all two groups of order up to 64. So that's quite a big calculation. we know that it's true if the depth and the Kroll dimension of the cohomology ring differ by at most 2. As soon as it differs by 3, our module theoretic techniques just aren't strong enough yet.
Would you conjecture it also with the minus I?
I would also conjecture it with the minus I, which is a slightly stronger statement, but in fact it should still be true. It's actually still true in all the examples.
And what does that mean about the Castelnuovo-Mumford regularity of the...
It says it's 0. I'll say that in a minute. So in fact, in terms of this picture, it's saying that there's nothing above this line in the E2 page of the Greenlee spectral sequence. So anything that is above this line, of course, has to die before you get to E infinity. But it's saying that there's nothing to die. So here's how you reformulate the quasi-regular sequences in terms of modules. So you remember yesterday what I did for a non-zero element in cohomology. I took a representative cocycle, which is a map from the nth kernel in the inner resolution of K to K, and we take the kernel of that map and we call that L sub zeta. So to say that zeta 1 through zeta r forms a quasi-regular sequence is the same as saying that multiplication by these zetas on the cohomology of these modules is injective for j at least n1 plus up to ni, and I gets added here, so that's why you should probably really have subtracted it over here. Because every time you move through one of these short exact sequences, you're going to do a long exact sequence in cohomology, and you get a connecting homomorphism, which is why you get a shift in degree. So every time you do a long exact sequence, you shift a degree by 1, and you end up with the condition that multiplication by the next zeta is injective on the cohomology of this module for j at least that bound. So actually, if I were to subtract I here, as I think we really should, I would have to cover up that. But actually, then it's quite a lot harder to prove this theorem if I cover up that I and subtract the I over there.
Can I ask a question?
Yes.
The proofs, the examples are you using Kadir-Vanishing theorem or something?
No.
So just kind of, it reminds me of Craig knows what I'm talking about. We have this way of thinking about the Kadir-Vanishing theorem that looks an awful lot like that. Condition.
I'm so ignorant, I have no idea what the Kadir-Vanishing theorem says.
Yeah, well, it has nothing to do with what this looks like, except for the way we wrote down, but maybe we should talk.
Yeah. I'll be very glad to hear about it, because any new tools that we can bring to bear on this are going to be valuable, because we're working in the dark here. Almost every bit of commutative algebra that I've ever applied to this, I've had to reinvent because I didn't know it. Right. And then, later I find out that it's something well known. So the other interesting thing is actually because of the way that you remember how varieties for modules work that I was talking about yesterday afternoon. The variety of one of these L zetas is just the hypersurface in the cohomology of variety defined by thinking about zeta as an element of the coordinate ring. So if you tensor these L zetas, you intersect those hypersurfaces. And by the time you get down to the r minus first, you've now got a module whose variety is just one-dimensional. And what that actually says is that the module is periodic. And it turns out, I mean, the group algebra is self-injective. This is one of the basic facts about the group algebra. So actually, eventually periodic implies periodic. And what that allows you to say is that that last element is automatically quasi-regular. So you only need to check the first r minus 1, and then the last one comes for free. And actually, modulo the last one, the quotient by all the parameters is 0 in at least that degree, is automatic. So you only need to check up to r minus 1, and then the last two things sort of automatically come out for you. And actually, there's a more sophisticated argument due to Okuyama and Sasaki using a rather delicate transfer argument that says that even the r minus 1 one is automatic. So somehow those last three terms are automatic. So actually, if the depth and the Krull dimension differ by at most 2, that says that any filter regular sequence is actually quasi-regular. So the existence of quasi-regular sequences is only ever in doubt if the difference between the depth and the Krull dimension is bigger than 2.
You seem to have the stronger version of quasi-regularity for the last element. Is it a typo or is it intentional?
Oh, that's a typo. Yeah. Oh, no, hang on, where?
After automatically?
Oh, automatically, zeta r is regular, and this is 0 for j at least, n1 up through nr. That's this stuff. This is h star modulo this sequence of parameters. This isn't the cohomology of the tensor product of the L zetas. Does that answer your question? Yeah.
So if you do have quasi-regularity, how careful do you have to be in choosing the sequence to get it to work?
Anything, if any sequence is quasi-regular, then every filter regular sequence is quasi-regular.
I see, okay.
So of course you can choose your sequence not to be filter regular and you're out of luck, but every filter regular sequence will be quasi-regular if anything is.
You have to fix the degrees for that, or is that just
No, that's
arbitrary?
that's arbitrary degrees. If there's any quasi-regular sequence at all, then every filter regular sequence is quasi-regular.
This is another question that sort of relates to what Karen asked. What do you know about the singular locus of these cohomology rings? Anything?
No?
What about in those particular examples where you can prove this? It's conjecture that there's always a
I really haven't thought about the singular locus, to be honest. I mean, part of the problem is I'm just a pure algebraist in some sense. I just don't know what geometry questions people have about commutative algebras. And part of the point of my being here this year is to learn from you guys what parts of commutative algebra are relevant to cohomology rings and try and understand that. What am I saying? Ah, yes. Yes, so one of the things that you get out of that is, well, you remember this theorem of Duflo, which says that the P rank of the center of the Celoff P subgroup is a lower bound for the depth. So the depth is always at least 1 whenever the Celoff subgroup is non-trivial. So actually, if the P rank of the group is at most 3, then the depth and the Krull dimension don't have room to differ by more than 2, and so there's a quasi-regular sequence. Well, you're probably longing for me to reformulate the quasi-regular sequences in terms of local cohomology, because they're just begging to be done that way. So let's define these AI invariants. So if you have a module over the cohomology ring, and actually, usually I'm just going to take M to be the cohomology itself. We're going to define AI sub the maximal ideal of M to be the maximum integer in which the ith local cohomology has something that doesn't vanish. So the local cohomology looks like sort of upside down Noetherian modules. So they start somewhere and then go down from there. The top non-vanishing degree is this AI sub M. And you then define it to be minus infinity if it vanishes all the way down. And so the interpretation of the existence of quasi-regular sequences in this context is that it's really saying that all these AI sub M's are strictly less than 0. And that's actually why I should have subtracted some i's there, so as to push it down to that s plus t equals 0 line. So,
Is there any reason at this point why you're sticking with the old definition of quasi-regular? Subtracting the I and being done with it?
Well, because actually subtracting the I only occurred to me after I wrote these notes.
But these theorems, do they hold? If you say
Yes, but I haven't written it up yet. The proof that you can move to the L zetas really takes some very delicate analysis of what happens in degree -1 Tate cohomology and lots of Massey products involving that degree -1 elements, and it's a mess. I have yet to put it in a form where I would like anyone else to read it. Whereas just with the old definition of quasi-regularity, it's all sitting there in the literature. But, I mean, eventually I do want to just replace the notion of quasi-regularity by this stronger notion. So where are we? Ah, yes. So the following are equivalent. There is a quasi-regular sequence. Every filter regular sequence is quasi-regular. The Dixon invariants are quasi-regular. That was actually proved in the last couple of weeks. And the local cohomology vanishes above the 0 line. So the reason why this is important in computation of group cohomology is because we can apply Grothendieck duality to this and get information about generators and relations. So if you reformulate this using Grothendieck duality, if you take a polynomial ring generated by a sequence of parameters in the cohomology ring. So the entire cohomology ring is supposed to be a finite module over that polynomial ring. Then if you're given a module over cohomology, like the cohomology itself, for example, you can look at it as a module over this polynomial ring and look at a minimal resolution. And we're going to define beta j of M to be the largest degree of a generator of one of these free modules in a free resolution. Okay? And you have to bear in mind that these generators for this polynomial ring are not in degree 1. So the usual way that the relation between the A's and the betas work is slightly shifted. And so actually the way it works is that there's a quasi-regular sequence if and only if the betas are bounded by the betas of the cohomology ring itself are bounded by the sum of the degrees of the generators. of this polynomial subring. So what that's saying is that not only all the generators of the cohomology are in at most that degree, but also all the relations for the cohomology as a module over that polynomial ring are in at most that degree. Now, if you want to think about the relations as a ring, you have to be a bit more careful, because actually you have to take pairs of module generators and multiply them together and see what happens. So those relations might have you might have to add two numbers that are at most this to get the degree of a relation involving two module generators. So actually what you get out of that is the following theorem. So if you have a quasi-regular sequence, then the generators have degree at most the sum of the degrees of your sequence of parameters, and all the relations have degree at most twice the sum of the degrees minus 2. I mean, it's minus 2 because this is really saying less than or equal to that minus 1. So actually, the way that group cohomology is calculated on a computer is that you calculate far enough to get a filter regular sequence. You can tell whether a sequence is filter regular by restriction to elementary abelian subgroups. So that's algorithmic. You can sit and do that. And you check for quasi-regularity, and you can actually do that using just a finite initial amount of the resolution. And then you can test that conjecture is true for that particular group, and then you know that you only have to calculate out to that degree. And in fact, there are slightly better bounds for the degrees of the relations which can be formulated using the subgroup structure. So in fact, you don't actually have to calculate quite out to that degree, but that's certainly an upper bound for where you have to calculate to. So it just tells you that you can stop when you've got there. So you're somehow, on the way to calculating the cohomology, you're verifying that conjecture for the cohomology ring, and then you know that you can stop. So finally, I'll come to the...
Now, if the conjecture turned out to be false someday for a group, then you would still see what the degrees... Could you still see what the degrees were from the restriction to the subgroups? You said you could test quasi-regularity or filter regularity at least by restriction.
That's a good question, and I don't know the answer.
Could you repeat that question?
The question is, if the conjecture were false and it turned out on computation that you didn't get a quasi-regular sequence, whether you could at least tell from the restriction subgroup method what degree you had to go to, what the regularity was, in essence.
I don't know the answer to that question. It's a very good question. So let's finally come to Castelnuovo-Mumford regularity. So if you've got a module over the cohomology ring, we're going to define its regularity to be the maximum over all integers j of, you take the top degree in which the jth local cohomology doesn't vanish and you add j. So because the generators for my ring are not in degree 1, the usual way of computing the a's and the betas has this extra term in it. You have to add in, you have to subtract off the sum of the degrees of the generators minus 1s from the normal formula that you would get for comparing this with the betas. So the regularity is the maximum of beta j minus that extra term. And there's actually a way of showing that in the top local cohomology, there's always an element in degree minus, so the rank of the group is R, so that's the Kroll dimension. And in the top cohomology, which is cohomology in degree R, there's always an element in internal degree minus R in that local cohomology. There's a very explicit way of producing it as a transfer from an elementary abelian subgroup. And that implies that the regularity of the cohomology ring is at least 0. Right? And actually then the conjecture says that the regularity should exactly equal 0. So this is effectively the conjecture that has been tested on all the 2 groups up to order 64 and a whole bunch of other cases. And this conjecture has some obvious generalizations, by the way.
What are the dimensions of the rings in that example? Are they always small, or can they be arbitrarily large? You said where the conjecture's been tested.
Where the conjecture's been tested, well, the groups of order 64, the maximum Kroll dimension is 6. But I mean, sorry?
That's the polynomial ring.
Yeah, that's a polynomial ring. That's not going to give you very much. But
So it wasn't that they were all 2 or 3?
no. No, there are some very interesting examples in there where some funny things happen. But still, this regularity is always 0.
Still, Karen, do you have examples where the dimension is truly large, the elementary subgroup is really big, where the conjecture has been verified?
Well, the problem is computation. As soon as the rank of the group is like bigger than 4, it's really, really hard to do resolutions because the resolutions grow so fast. The rank of the group, the maximal rank of an elementary abelian subgroup, tells you how fast the cohomology is growing. It tells you the polynomial rate of growth of the minimal resolution. And so if your rank is large, your polynomial rate of growth is going to just overwhelm your computer resources very quickly. So you know, you're going to end up only being able to compute, say, the first 10 terms of the cohomology ring, and that's not enough to get up to these bounds where you need to get to compute the cohomology ring. I suppose in future generations where we have bigger and better computers, that won't be such a problem, but well, the extra special 2 groups are Cohen-Macaulay. It's sort of automatic there. I mean, they have arbitrarily large rank, yes, but for Cohen-Macaulay cohomology rings, there's nothing to prove. The regularity is automatically 0.
Why is that? Because the AD, the dimension one, doesn't.
You
wouldn't get a problem at the top spot, no?
For a Cohen-Macaulay cohomology ring, the only local cohomology that doesn't vanish is the top degree,
right.
And its top, it's Gorenstein with the top local cohomology being in degree minus the Kroll dimension. So this element that I produced here, that is actually the top degree in the top cohomology in that case. So, I mean, that's part of what that Greenlee spectral sequence tells you. It tells you that in the Cohen-Macaulay case, the local cohomology is just the matless dual of the ring stuck so that the identity element plops over into degree r comma minus r.
That's interesting. So that says if that's Cohen-Macaulay, it's a polynomial ring.
No, it says it's...
And it's generated in degree 1.
Yes, absolutely. And that's a very nice corollary of this, is that if a cohomology ring of a finite group is a polynomial ring, then the polynomial generators have to be in degree 1, and in fact that forces the group, it forces the prime to be 2 for a start, because otherwise degree 1 generators square to 0, and it forces the group to be essentially an elementary abelian 2 group. You're allowed an odd order normal subgroup, which doesn't affect the cohomology, but
you actually know this conjecture for the Cohen-Macaulay case.
Oh yes, absolutely.
One last
yeah.
In fact, you have things of every dimension.
Yes, yes, that's right. Yeah.
In every dimension, but not, well.
What we don't have is examples where the depth and the Kroll dimension differ by a large number. That's really what we're lacking. We'd really like to understand some examples where the difference between the depth and the Kroll dimension is large. It's very hard to write down such examples that you can compute.
When you say we, are you talking about yourself, or are you talking about...
Most of these computations are me and John Carlson. Well, these conjectures generalize in an obvious way to various other classes of groups. So I guess if you have an orientable virtual Poincare duality group, whatever that might be, so things like SLNZ would be an example of that, then the regularity of the cohomology group should exactly be the dualizing dimension of the group. It's probably easier to understand what the compact Lie case is saying. For a compact Lie group, if you have a compact Lie group of dimension d, there's actually an orientation issue. If you think about the Lie algebra of the compact Lie group as a module for the group, so there's a conjugation action of the Lie group on the Lie algebra, that action needn't be orientable. So, I mean, you might have to go down to a subgroup of index 2 in order for that to be orientable. So there's this character with values in plus and minus 1, which gives the orientation of the action of the group on the Lie algebra. So that's just some one-dimensional representation, which you can then sort of translate into a representation over K, if you like, just because it has values in plus and minus 1. So that representation is called epsilon. And actually you need the version of the Green-Lie spectral sequence that works for compact Lie groups abuts to the homology of BG with coefficients in epsilon instead of in K. So the natural thing to do is to conjecture that the regularity of the cohomology ring of a compact Lie group with coefficients in that funny orientation module is negative D. The orientation module, of course, is trivial in a lot of cases, like for finite groups, and for connected compact Lie groups is trivial, and so on. But, for example, if you take the orthogonal group of 4x4 orthogonal matrices, you'll find that the orientation module is actually non-trivial. And actually, you get the wrong answer if you look at the regularity with trivial coefficients there. So I guess I should give you an example, just to show you that we have actually computed something non-trivial here. So take for example the group E6. Okay. So this is a compact Lie group of dimension 78, and I'm going to talk about characteristic 2. Now the cohomology of BG with coefficients in a field of 2 elements was actually computed in the 70s by Kono and Mimura. They actually didn't quite complete the computation. They had one undetermined coefficient in a relation somewhere. But that doesn't affect the local cohomology. With both values, 0 and 1 for that undetermined coefficient, you get exactly the same answer for computing the local cohomology. So actually, in this case, the Kroll dimension of the cohomology ring is 6 and the depth is 5. And if you look at the A invariance, A5 is minus 90, and A6 is minus 84. So you've got to take minus 90 plus 5, so that's minus 85, and minus 84 plus 6 is minus 78. So you have to take the biggest of those. So that's minus 78. Ah, good. So minus 78 is minus the dimension of the compact Lie group. So it works for E6 in characteristic 2. And in fact, it again works whenever the difference between the depth and the Krull dimension is at most 1. For compact Lie groups, we don't know how to get as far as difference 2 because we just know so much more about modules for finite groups than modules for